Hello friends, welcome to class 2 lecture on Introduction to Finite Element Methods and its applications to aerospace structures. Since we are in the beginning of the course FEA of aero structures, it is really important for you to understand the basic aspects of finite element methods and also its applications. So today I am going to speak to you on the fundamental, which is the basic theory of the FEM, and its applications to especially to aerospace domain. And later on, towards the end of the class, I'll be discussing the latest trends and practices that is being followed within the aerospace industry. So any aspiring stress engineer or finite element engineer, it is very important for them to understand the concept of the finite elements and its applications. So with the availability of the latest finite element tools and commercial packages in the market, so sometimes the physics behind or the concepts of these finite element methods might be completely lost, and the user might be handling the data which is full of contains mistakes and errors. So one has to clearly understand the concepts in their mind and then use it, and in order to achieve the best possible results. So let's quickly jump into the slides. So first of all, the history of FEM goes back to the 1950s and 1960s, where the first finite element methodology was coined by Clow, and then later on the mathematical methods were developed and it was released in a book format by Zinkovich and Chung. And later on, during the 1970s and 1980s, all the finite element software packages came into came into the market, and like this Nastran and Patron, whatever we are going to see in this course, like came around 1969, which is pretty much 1970s and 1975, when two scientists of NASA, they used their coding, whatever they coded in order for the mathematical calculations within their company and for their work, and they came out of NASA and they improvised it, and they officially released as a Nastran and Patron. So that's how the finite element, the commercial packages and the software packages came into existence, pretty much somewhere around the time of 1970 and 1980. So before we move on to understand the concepts of finite elements much more deeply, much more in detail, so for any stress engineer, as I mentioned earlier, it is necessary to understand so what types of inputs we give into the finite element model, and what types of output that is needed, or what types of output that is needed, we can expect from the mathematical model. On the right, you can see that there is a finite element model, which is the mathematical model or the mathematical representation of the actual structure, physical structure, where we give in geometry, which is the geometry properties, your area, moment of inertia, and the dimensions on these things go into the geometry input. And coming to materials, it's the material properties, your Young's modulus, Poisson's ratio, and shear modulus, and various different things for various different materials. If it is isotropic, then you have a set of parameters, and then if you are modeling a composite, which is a typical orthotropic and anisotropic, you will have a lot more parameters, or because the properties depend on the different directions. So you have similarly have the different stiffness properties. So similarly, loads and boundary conditions, this all being fed into the model. The model itself is a representation of the stiffness. You can imagine a simple mathematical model as a spring mass system, or a collection of springs that being put together. So when you feed these parameters in, and what you're expecting is obviously the unknown quantities such as displacements and loads. Displacements, which is nothing but the strains, and loads, which is forces and the internal reaction, suppose you want the free body loads and etc. So most of the aerospace industries, what they do is like they use the finite element model, and at the same time they do the testing of the actual product, and then they correlate the results from the finite element model against the test results, just to prove that the model works perfectly, the product works perfectly, the validity of the product basically. So if you look at the process flow, it is the concept starts from the design boards, where the engineers come up with a concept, and then slowly they move into modeling, how they can model these things, how they can model the concepts, how they can model the design into the into their specialized software such as finite elements, or if it is CATIA design softwares, CATIA Creo. So how they can model it, and then finally, and using mathematical calculations also, sometimes they can do analytical models. So this modeling and simulation steps come later in the design, when they try to come up with the something on paper, and then finally they, once the model is ready, they go for analysis. They have to do the analysis just to check how the model behaves under for certain conditions, for certain loadings. Either it may be a structural model, or either it may be a thermal model, so, or either it may be a dynamic model. So they have to analyze, and they have to have a clear understanding how the model behaves. And then once these steps are being done, and once they come out with the results of the analysis, based on that they go back and they modify the design in case if it is failing or something, and then finally they go for prototyping and testing. They develop a prototype, and at the same time in parallel they do testing. So in terms of testing, they would do it for the laboratory conditions, whatever the best possible laboratory conditions, which is reasonably close to the real time conditions. And if there is a failure in the test, again they go back to the design stage, and then they modify their models, and then they have to run the analysis simulation again, and then coming to the testing. So each company will have its set of criteria to meet for the testing, and the results of the analysis simulation, whatever they carried out, should correlate with the results of the testing. In a typical scenario, for example, the major player in aerospace industry is Airbus. So one of the major players, I could say. So we used to test the aircraft wing structure and aircraft interior structure. They have a set of criteria, displacement criteria, and strain criteria. So they would expect at least plus or minus 10 percentage correlation of the test results with the analytical and numerical models. So if it falls outside the 10 percentage, then there will be a detailed investigation whether there is something wrong happened at the test, or there is something at the test setup. And finally it boils down to the model. If the model is not working properly, then we have to tweak and come up with the stiffness model such that the results of the test and the results of the analysis are well within plus or minus 10 percentage. Once the testing is satisfactory and testing is passed, and there is no failure of the component, and no visible damage, or if it sustains the damage for 3 seconds, usually if in aerospace structure they have a fail safe structure and safe fail structure. the high level FAA Federal Aviation Regulations requirement is the structure should withstand the ultimate loading at least for 3 seconds without any permanent damage or permanent deflection. So if the testing is passed, so finally they go for fabrication, because usually the prototypes are mainly tested, and then they don't use the prototype for once the test space is done, and they store it for their future reference, and they generate the test reports saying so and so conditions and so outcome was arrived, and then finally they go for fabrication of the parts. And then again during the fabrication there might be an voids, or there might be errors, or there might be damage. So again, if those things result in during fabrication, then they have to check their quality documents, and finally mitigate how they can overcome these defects. And then sometimes it might happen that during fabrication something, a serious defect happens, and then it slipped through all this process, and finally they go back to the design, and then they come again. So in that way this aircraft industry is like, at the moment it's working. So especially the original equipment manufacturers, who are releasing their product, they are uh, very careful in releasing, because the federal aviation authorities, they really scrutiny the scrutinize the products in terms of quality and in terms of defects. So really we should be careful in having in mind that quality is the utmost important thing in the aerospace industry. So in order to achieve the quality, one should, and especially for the stress engineers, for the finite element engineers who are undertaking this course, should have it in mind very clearly that one should use a proper mathematical concepts to arrive much more closer results to the actual scenarios, so that the later stages such as manufacturing will be pretty easy and smooth. So let's now go into the fundamentals of FEM. Okay. So in a overall mechanics scenario, there are two methods. One is the exact method, and other one is the approximate method, very obviously. And exact method is nothing but the closed loop analytical solution, which is the strength of materials or the mechanics of materials. And the approximate methods are nothing but the numerical methods. So this finite element method falls within the approximate method, falls into the category of approximate method, I would say. So looking within the finite element method, a physical structure or a physical phenomena is being modeled using a set of mathematical equations, which is called governing differential equation, which might be a differential equation or a partial differential equation. And finally we use a set of methods to solve the equations, and for a set of boundary conditions. When you say boundary conditions, it might be an displacement value, initial displacement, or initial force, whatever that is being applied to the structure. And then we come up with the solution. Once the equations are solved for the set of conditions, we arrive at the solution. So there are different methods for solving the physical phenomena of, or solving these equations. So one of the method is the finite element method. I have listed down the various methods that have been that are available in the current scenario, which are finite difference method, finite element method, finite volume, boundary element method, spectral, and perturbation method. So I'm not going to speak to you on all these methods as the time doesn't permit. So I would like to speak to you only on the finite element method. But to give you a very brief, like finite difference and finite volume are mostly used in the computational fluid dynamics, CFDs, or fluid mechanics, and the boundary element method is slowly developing within the structures domain. And there are few methods called as spectral and perturbation method. Perturbation is nothing but the small displacement method, and these two are still under the research, still under research. So there are not much of these things. And also there are, apart from these methods, there are meshless methods that is being still developed or still being investigated by the wide community of researchers and scientists. Whereas in the finite element method, again finite element method is classified into the direct approach, which is the stiffness matrix method, and variational approach, and then the weighted residuals method. So these are the three categories of the finite element method. Starting with the direct approach and stiffness matrix method, the commercial packages or the software tools like Abacus, ANSYS, Nastran, Patron, Hypermesh, and whatever in the market, they use a combination of variational approach and the direct approach. It is the uh, it is the mixture, or it is the both methods combined together. Suppose, for example, they start with the variational approach by selecting a polynomial equation for a displacement field, and then once the polynomial equation has been selected for a particular displacement field for the model, and then the equation is solved using the direct matrix method. To put it in much more simpler terms, imagine a structure, imagine a cantilever beam that is being modeled into the that is being modeled into the your software. So the cantilever beam can be broken down into smaller elements, say 1D elements or 2D elements. So based on the type of element you select, the polynomial equation is formed. So in your finite element course in the engineering, you might have come across two types of refinements, which is H refinement and other one is P refinement. H stands for the increasing the number of elements, and P stands for polynomial, which is the, if you are using the higher order elements, a simple quadrilateral, suppose in the finite element terminology, in the you use a simple rod element which has two ends, one is two nodes otherwise, and there are some higher order elements which might have three nodes for a same rod element. There will be a mid node between the two nodes. Suppose if I scroll down and show you, suppose imagine a quad element, a simple quad element here. Suppose the higher order element will have a mid side node. So there will be, instead of 4 nodes, there will be a 8 nodes. So that's what I meant to be here. So based on the polynomial equation, once it is selected for the displacement field, and then they use the stiffness matrix method to um, directly I'm sorry, they use the stiffness matrix method for directly solving the those equations and then arriving at the results. Coming to variational approach includes the minimum potential energy method or the Rayleigh-Ritz method. Both uses potential energy function in which your displacement function is chosen by the user for the entire domain, which is the structure. and it is in the form of a polynomial equation. And then what happens is like and then they solve the equation to find the unknowns are nothing but the displacements and forces. And similarly, weighted residuals method, where weighted residuals method in which there will be, you have an equation which is very approximate, and then there will be functions of both independent variable and functions of constants called residual. So in order to minimize the residual, you have to select, yeah, you have to select a equation, proper equation that is used for minimization of the residual. It's very difficult to put in terms of words, but if you gone through the examples, like during your when you take your finite element course, probably it might be easy for you to follow up and understand. But within this course, I'm going to speak to you on the very basics and introduction of this topic. So we have to give you a very quick recap, or to put in a nutshell. So these three methods are available at the moment, and within each method, for example, variation method, there are two types, which is minimum potential energy. Potential energy is based on the your strain energy and work done. And Rayleigh-Ritz method is also uses the potential energy function. And weighted residuals, it's being subcategorized into Galerkin method, subdomain, and least square method. So at the minute, for the commercial packages and softwares, we use the direct stiffness matrix method combined with the Rayleigh-Ritz method. So it is same as the ones which I explained a minute before, where uh, you have the finite difference method, and then from the finite difference method, this was the name of the mathematicians or engineers who coined these methods. And then finally, the present day finite element method, which will have the all the little bit of all the functions, little bit of it, it touches the all the aspects of the typical pure mathematical methods, such as variable methods, and then uh, the direct stiffness matrix methods. So this present day finite element methods was first coined by Clow in during the year 1960, and then from where it came into the market. The one because of only the reason that it is very easy for coding purpose. They can make it into a computerized program, because matrix equations or a set of algebraic equations that can be coded very easily. Okay, now moving on to FEM. So what is FEM? FEM, it's deals with the, as you know, we have already discussed that it's a numerical method, it's an approximate method, and there are various different techniques. That's all fine. So it has a domain which is being broken down into small subdomains. This is a domain is called a structure, big structure, or the global structure, that's being broken down into small elements that are being interconnected at some points called nodal points or nodes. So whatever the functions, such as displacement, forces, they will all be computed at the nodal points, and each nodes of the elements should satisfy certain conditions called compatibility conditions. It should be compatible to the nearby element or the connecting elements, I would say. Suppose you take this element which is in the middle, it should be compatible on its edges to the to its surrounding elements. If it is not compatible, that means there may be a discontinuity or there is a void in the system. That means the flow of displacements and the flow of functions is not smooth. So since the domain is broken down into multiple subdomains, this is called piece. We are breaking down the structure into small pieces, so it's called piecewise polynomial function. That's why the polynomial equation is called piecewise polynomial function. So from an infinite degrees of freedom, a complex structure or a big structure might have the infinite degrees of freedom. With the proper selection of elements and breaking down into the defined number of elements, we are bringing down the infinite degrees of freedom to finite degrees of freedom. So it is whatever we I have explained earlier. So first one is the domain is being divided into small and simpler elements, and then the field quantity is interpolated by a polynomial equation. A field quantity is nothing but your displacement or force. If it is a displacement method, displacement is unknown. If it is a force, force is unknown. And then the connectivity of the nodes to the neighboring elements or the surrounding elements, it should satisfy the compatibility conditions. And this is very important over here. So I have put down the governing differential equations to show you some, have a feel for different types of problems. One is obviously the solid mechanics problem, other one is the fluid mechanics, other one is thermal and electrical. These are the different areas where the finite element can be used, and this represents the actual physical phenomena. For example, the solid mechanics, there is a bar that is being loaded axially. This is the governing differential equation of the bar. Du is the u is the displacement quantity, which is the field quantity, and these governing differential equations or can be the I'm sorry, these physical phenomena uh, are represented mathematically into the finite element software by these governing differential equations, and we apply the boundary conditions, which is the initial value problem or the final value problem. It depends on the set of criterias, and then once the boundary conditions are assigned, and then these differential equations are converted into a set of algebraic equations. There are some techniques, they convert the uh, governing differential equations into a set of algebraic equations, and finally the algebraic equations are solved using the matrix method. So it combines the polynomial equation of the field quantity, and at the same time it uses the direct stiffness matrix method. So the global finite element equation is represented in this format, which is k, u and f. You might have noticed that k is in the square bracket, which is a scalar quantity, which represents the stiffness of the structure. Both geometrical and material properties come into k, and u and f are in the open brackets, that represents the vector quantities. So and this one is the scalar, and these two are the vector quantities. So what we are giving the governing differential equation, which is nothing but the physical phenomena that is represented into the model, that is being mathematically modeled, and then finally the application of the boundary conditions, which is the loads, either loads or it may be a displacement, or it may be a temperature in terms of thermal or the heat flow, or it might be in terms of fluid mechanics, it might be a pressure, fluid pressure, and in terms of electrical, it might be a current flow or conductivity type of thing. So that is being applied, and then finally we generate these equations which is being solved using the matrix method to get the unknowns. Unknowns might be displacements and forces. So it is the same thing as I mentioned earlier, that the mathematical model can be represented by a simple spring mass system, where spring represents the stiffness, and the instead of mass you can directly apply the load. It might be a load or it might be a small perturbation, which is a displacement, and then finally the internal forces are computed. So over here I have put an example to show you the flow of the steps within the finite element process, where a cantilevered bracket which is being applied uniformly distributed load, and then finally what I'm doing is like I'm idealizing the structure as a region, which is a domain, and which is a defined region, and then I'm selecting the element type, and then I'm also selecting the order of the elements, which is the lower order or the higher order elements. Based on the type what I'm selecting, I'm meshing the domain. I'm breaking the domain into small piecewise subdomains. I'm meshing the region into using the elements, and then finally I'm applying the loads and boundary conditions, which is the since it is a cantilever beam, it is these nodes will be arrested for both translation and rotation to be 0, and finally I'm applying the loads, and then what happens over here is I'm getting the displacement plot showing the displacements. Maximum displacements will be at the corner, the cantilever beam, and also the stress field over here. So it is, these are all the steps within the finite element analysis. So the finite element tool is a very powerful tool that can be used to predict the displacements. It can be used for any free body loads. Suppose you take the cut, and then you can have the free body loads, and then for the support reactions, and then also it can predict the material failures based on the your material properties. So it's a very powerful tool that should be carefully used, so otherwise it will be error prone. So coming to the advantages and disadvantages of FEM. FEM can handle a very complex problem. When I say complex, it can be in terms of complex boundary conditions or complex loading, and then huge variety of problems, as you saw it earlier, like it can be solid mechanics or fluid mechanics, or can be thermal analysis and the structural analysis, civil structural analysis. A huge variety of problems can be solved using the finite element method. But whereas the disadvantages is, it is end of the day it is an approximate. It's not as close as the your analytical methods using the strength of materials or mechanics of materials, but it is reasonably close to whatever solution your analytical method gives. And finally, FEM is time consuming, and then cost, it is on the higher side, because you need the higher computational power, you need the equipments to run the FEM, and then it is time consuming. Like in very complex models might take a longer time to solve, so it is time consuming, and it's not cost effective.